for the audience, the final speaker that we have for this evening is Maria of CNRS France. Maria is currently a PhD student in electrical engineering and is developing photovoltaic-based microgrids. She was recognized for her outstanding academic record at Comillas University and was awarded an academic excellence scholarship during her undergrad education. Further, she is part of the international working group investigating the technical challenges associated with the operation of microgrids. Today, she will share with us her fascinating work on photovoltaic-based batteryless systems to support the temporary islanding of electrical grids.
Hello, my name is Maria Candelaria Utrilla, and I'm currently pursuing a PhD degree in electrical engineering at Grenoble's Electrical Engineering Lab, also known as G3 Lab. To present my research, it's important to start by explaining that traditional grids are undergoing a revolution. Here you have the scheme of a typical traditional grid. The electricity is produced by large-scale power plants that are connected through transformers to high-voltage transmission grids. These grids are composed by high-voltage lines that allow to transport the electricity through long distances while avoiding major energy losses. In turn, the transmission grids are connected to distribution grids, whose objective is to distribute the energy to the final consumers. Big consumers, such as industries, are connected to medium voltage lines, and small consumers, such as households, are connected to low voltage lines. The important thing about these grids is that they are one-way routes, because the power always flows from the transmission level to the distribution level. However, as I said before, traditional grids are undergoing a revolution, and this is because there is currently a massive integration of renewable energy plants. There are large-scale renewable energy plants that are connected directly to the transmission level, and there are also medium and small-scale plants connected to the distribution level. And the later, the small and medium plants are the ones actually causing the revolution, because they are making the power flux direction change. So in current grids, power can go from the transmission level to the distribution level, but also from the distribution level to the transmission level. On another note, there are several events that may force the opening of a distribution line and in consequence may generate the isolation of all the grid downstream. These events can be, for example, extreme weather events or grid failures. You may think that because of the renewable energy integration, this is no longer a problem, because whenever a distribution grid is isolated, the renewable energy produced by these plants can be used to feed all the consumers placed here, which are also, these consumers are also called loads. However, this is not the case. Up until now, whenever a distribution grid is isolated, the power is cut for all the consumers here. Why is this? It's important to know that for a grid to work properly, there needs to be at least one agent making sure that the voltage amplitude and the frequency are stable. So one agent that fulfills the voltage and frequency regulation functions. In traditional grid, these agents are the large-scale power plants. And in current grids, even though there are other power plants here, they have not been conceived with these voltage and frequency regulating functions, because they have been conceived thinking that the distribution grids would always be operated connected to the transmission grid and in turn connected in turn to large-scale power plants. So up until now, whenever a distribution grid is isolated, these renewable plants turn off and the power is cut for all the consumers downstream. However, grid operators are increasingly interested in enabling the isolated operation of the distribution grids. I am the co-author of an international CRED report that has analyzed several European demonstrators built by grid operators that test the isolated operation of distribution grids. And in this report, it is explained that several common solutions have been developed to enable the isolated operation. One typical solution is grid reinforcement. That is, to build several parallel lines so that if one needs to be open, there are other lines that always connect the distribution grid to the transmission grid. However, this is a rather costly solution and not always cost-effective in rural areas. Another solution can be to bring emergency diesel generators that can fulfill the voltage and frequency regulating functions and that can be connected to the affected area. But these generators cause CO2 emissions, and there may be long waiting times to bring the generators to the affected area. Finally, a common solution is to install permanent batteries that can fulfill the voltage and frequency regulating functions. However, these batteries, even though they are deploying and they are being developed very rapidly, they remain very costly for the moment and they cannot be installed at large scales. What we propose in my research is to change the software of the renewable energy plants so that they can fulfill the voltage and frequency regulating function, and therefore they can feed the loads during isolated operation. This is a solution that can be regarded as a compromise, because you may tell me that it has one important disadvantage, that is time limited. So this means that the isolated operation can only last as long as the energy available from the renewable sources is enough to feed all the loads placed here. However, it has also very important advantages that make the solution very attractive for operators. On one hand is that we only have to change the software of the renewable plants and not the physical assets, so it requires a minimum investment. This makes the solution very easy to expand to various areas of the grid and to deploy it at large scale. And in the end, thanks to this solution, we will learn how to control the renewable energy plants in the best possible way and to optimize the available energy. This means that in order to make the isolated operation last as long as possible, with this solution, we will learn how to use the available energy in the best possible way. There are various scientific challenges arising from the system that I propose. One of them is how to change the software of these plants to implement the voltage and frequency regulating function. But this is something that is mastered both by scientific research and in the industry. Another challenge is how to ensure that correct and secure transitions between the grid-connected operation and the isolated operation. But the demonstrators have already shown that these transitions can be correctly achieved with existing equipment in the grids. However, there is a third scientific challenge that has not been correctly addressed by the literature and that provides us a research gap. This is how to implement a power sharing strategy among the different the various power plants existing in the isolated grid. What does this mean? It means that if at each time instant all the consumers of the isolated grid will be consuming a certain amount of power, and we need to and there needs to be a strategy which decides how much power each renewable energy plant produces to to feed all the loads. What we want to do is to implement a decentralized strategy. This is a strategy that does not rely at all on communication. So that does not imply building communication channels, which are costly, between the different renewable energy plants. How are we going to do this? By reinventing a very well-known power sharing strategy, which is called the group control. So this is kind of difficult to explain without going very much into the technical details. But what we need to understand is that the frequency is a unique magnitude for each grid. So in a grid, each power plant can impose a different frequency. So solar plant 1 can impose a certain frequency, and solar plant 2 can impose another frequency. However, the dynamics of the grid will force both solar plants to reach a consensus. And in the end, in a steady state, both plants will always finish by imposing the same frequency. So, since frequency is uniform for each isolated grid, it can be used as a communication vector. Here you have a diagram representing the frequency versus the power output by each power plant. And the orange line represents the control law of solar plant 1. So solar plant 1, what it does is that at each time instant, it measures the power that is outputted, that is being generated by the solar plant, and it decides which frequency it should impose. And this is the same for solar plant 2. So if there is a certain load, power demanded by the loads, which is represented by P loads, we can start with a situation in which solar plant 1 produces this power and imposes this frequency, and solar plant 2 produces this power and imposes this frequency. And to note that P1 plus P2 is equal to P loads, so to the power demanded by the loads. However, this situation is not will not last, because, as I said, the grid will force the solar plants to reach a consensus, and at the end, an equilibrium will be reached, in which the frequency is the same for the whole grid, and each power plant is producing a power which is proportional to the maximum power available for each plant. So, as I said, this is a very well-known power sharing strategy that has been applied for decades with large traditional power plants. However, if we try to adapt this strategy to renewable plants, there is a major challenge. It is that the maximum power available varies because of the ambient conditions. For example, the maximum power available in solar plants varies with the solar irradiation. That's what we are trying to develop: adaptive group control, adaptive group strategies that can resolve this issue. Another problem is that stability issues can arise in the grids if we use adaptive group controls, and this is another issue that I'm facing and that I'm trying to resolve. Stability issues is mainly the fact that there can be big oscillations of frequency of voltage and current in the grid, and that can damage the grid assets. And finally, another issue that I'm trying to resolve is that most researchers, for the moment, they use very simple models for the power plants. And what I'm trying to do is use very detailed modeling of the photovoltaic dynamics to have better quality power sharing strategies. So, some preliminary results that I have for the moment is that I have achieved 2 new adaptive group strategies, which are yet to be published, and that they achieve an optimization of the available photovoltaic power They allow to maintain stability, and they are easy to implement. Another result of my research is that I have managed to develop a simplified photovoltaic model that takes into account the detailed dynamics of the photovoltaic cells, but it's simple to implement, and therefore it allows to simplify the whole process of designing the group strategies. Thank you very much for listening. Hope it was not very complicated. And I would like to thank the NTU and CNRS joint program that has funded this thesis, and also my thesis supervisors and all from D3 Lab, and all the collaborators from NTU and the University of Western Australia. Thank you very much.
So thank you, Maria, for that very interesting talk. So similarly, again, we invite any questions that the audience might have for Maria.
Thank you.
Thank you, Maria. So while we're waiting for questions to come in from the audience, Maria, just wanted to ask maybe a bit of a naive question, but given like solar and electric vehicles, being on the uptrend, and I'm assuming that these will have an impact on the grid. So I'm just wondering, how does your work help in a bit of that future, right? Like the rise of electric vehicles or the increasing use of solar. Does your work have some impact on these industries, or the impact on the electrical grid?
Yes. So my work is mostly related to the increasing of the solar industries. So what I propose, as I try to explain broadly with my presentation, is to use the already installed photovoltaic plants to be able to operate the certain sections of the grid in an independent way from the main grid if necessary. So what we expect, relating to your question, what we expect more and more is to have more and more installed photovoltaic plants everywhere. For example, in France, where I actually do my PhD, or in Spain, where I come from, we are currently, and for years, we have been seeing how rural areas are being being subject to a huge increase of these solar plants. And what we want to do is, what we propose to do is to use them in a more intelligent way to help the grid operators in difficult situations. So regarding the electric vehicles, it's kind of a separate question that we don't address in my research, but of course it will be a challenge, because we expect a growth of these and a tremendous growth of these vehicles, and they will, of course, impose challenges of the grid because of the recharging needs of these vehicles, but they can also lead to opportunities. For example, we can think that in the future we may be able to use the batteries inside the vehicles as flexibilities for the grid. And let's imagine that in a situation when we have an emergency and we need to isolate a certain section of the grid, we can use the photovoltaic plants with my solutions during the day to operate this isolated grid during the day hours. And during night hours, maybe the vehicles that will be connected to the isolated grid can be discharged. And thanks to that, there can be some consumptions in this isolated grid, even if we haven't resolved the faults and we cannot be connected to the main grid. So yes, there are things to do.
Great, yeah, thank you. Very good insights. We do have a question from the audience. I'm just going to read it out. So audience member mentioned that it's a very interesting talk. So thank you, Maria. And the question is, he's just curious about at what circumstance the microgrids may be unplugged from the main grid. Okay. And the following question is there a safe system to manage these?
Yes, okay. So at what circumstance? There are several possible circumstances that can lead to the isolation of a part of the grid. The most common is, for example, the need. So these the scenario where my solution most applies is the case of a rural grid, where it's not profitable to build many lines. So we have one or several villages that are connected to the main grid through one line, just one line. And the problem is that whenever we need to do a maintenance in this line, these villages have to be decoupled from the main grid. And as I explained in my presentation, if you are decoupled from the main grid at this moment, even if there are photovoltaic plants there, you cannot continue the supply. So the situation that would lead to a decoupling would be a great failure. For example, due to a weather event and a storm, a tree falls into the line and the line needs to be disconnected, or a simple maintenance that has to do every now and then on the grid. And just to add that we are not this solution seems more and more attractive because we are now seeing how extreme weather events are more and more often. We can think about, for example, the California fires of the last years. And there was a second. The second part of the question was if there is a system that can safely manage the transitions from grid connected operation to isolated operation. And yes, there are. There are, as I think I explained in the presentation, is that I am part of an international working group that is analyzing several projects that have already tested this isolated operation, and they have demonstrated that with current industrial products, we can safely manage these transitions. The problem is that sometimes they are costly. You need to put extra sensors, extra protection devices, etc. And what my solution tries to do is, the philosophy behind my solution is what can we do with what we can do with what we have already in the grid. And that's it.
Great. Yeah. Thank you so much, Maria, and thanks to the audience for this wonderful discussion. So if there are further questions, I think offline, Maria will also certainly welcome them. But thanks again, Maria, for your time today and wonderful presentation.
It was wonderful, and thank you for the opportunity.